free response problem. Example 2, thinking out loud. Now, pay particular close attention to the thinking out loud. There are a lot more concepts to consider here, especially with the addition of a capacitor later on in the problem. Physics students are analyzing the circuit to the right. A variable DC power supply is connected to an ammeter and 3 resistors. The resistances of 2 of the resistors are known to be R2 equals R3 equals 50 ohms, but the resistance of the third resistor, R1, is unknown. The students collect data on the potential difference across the power supply and the current measured by the ammeter as follows. Now, before we get into the problem, let's get an idea of what's happening in the circuit. Current leaves the battery, big I. The ammeter, it will be measuring those values. And here's the point of interest. At junction B, the current will divide and divide I2 slash I3. The current through R2 is the same current through R3. The two are in series. And then the current through R1, let's call that I1. So, and that's the point. The current's going to divide there. But what I want you to understand is that these 2 resistors are in series. R2 and R3 are in series, but in parallel with R1. Okay, so knowing that helps. All right, on the grid below, plot the data points for the current as a function of the potential difference. Clearly scale and label all axes, including units if appropriate. Draw a straight line that best represents the data. Now notice on the y-axis, I converted current from milliamps to amps. I just wanted to get it out of the way so I didn't have to worry about it later. So I tend to forget to convert, so I'm doing that now. And know that the slope of this line is the change in current over the change in voltage, which will be equal to the inverse of R equivalent of this circuit. So that's the important thing here. Notice the data points are plotted in red. The green line is the line of fit. It's a judgment call when you're drawing a line of fit. You're trying to minimize the vertical distance that the red points are from the green line. I chose 2 points on the line with the X with the circle around it. That's very important. Use data from the green line, your line of fit. My data pairs are here, and make sure you populate the change in current versus change in voltage. And the inverse of that slope will be the equivalent resistance. Oh, yeah, I wanted to show you my project this past weekend, that I'm not just a physics teacher, but I do other stuff. I had a yard cart, a lot of mulch to move, and that cart was not going to stand up to the abuse. I took it apart, cut up some plywood for the new structure, and then I added a license plate, kind of snazz it up, so it's street legal, and it's a bicentennial edition Pennsylvania license plate, found hanging in my garage. All right, moving right along. All right, calculate value of R1. So we know R2 and R3. We know the equivalent resistance from the slope of the line. And so resistors in parallel, 1 over R equivalent is equal to, in this case, 1 over R1 plus 1 over the combination in series, 1 over 50 plus 50. So that's the equation being applied to resistors in parallel, but we have 2 resistors that are in series. 132.56 ohms is the answer. The power supply is now fixed at 12 volts. Calculate the current through R2. Now notice that I have a chart here, and this helps me keep track of things. Sometimes I'll fill it out if I got a little time. I'm not going to fill the whole thing out. This problem has enough parts to it that you don't need to calculate everything. Enough parts in terms of the concepts they're asking you to grapple with. But R2, if you know, as the adage goes, if you know two things, you can find the third. So if you know V2 and R2, you can find I2. So the voltage across R2, we know to be 6 because the voltage is going to divide in these two resistors. But knowing that the total voltage across both resistors is 12 volts, which means R3 has a voltage drop of 6 volts. So voltage divides when it comes to resistors in series. And whether we need to know that or not, but the voltage across R1 is 12 volts. So you could fill out this chart for a few of the values, but you don't necessarily have to calculate all of them. So R2 has 6 volts across it, and we know the resistance of it. So 6 divided by 50, 0.12, or if you're of the mind that you can take both R2 and R3 in the aggregate, and we have 12 volts supplied to it and divided by the total resistance in that branch. So you know the current will be 12 over 100. Same answer. Just depends how you look at it. All right, moving on. Resistor 3 is now removed and replaced by an open switch in series with an uncharged 4 nanofarad capacitor, as shown below. The power supply is still fixed at 12 volts. Calculate the current R2 immediately after the switch is closed. And when I think immediate, 10 to the minus 64 seconds at that moment. Now, the current through R2 is going to be the same whether that capacitor is there or not at the instant that the switch is closed. So know that up front. The capacitor is ready and willing to accept charge. It's empty. So the current that's going to rush, the inrush current through R2 is going to be a maximum. And then over time, as the capacitor begins to fill up, current will cease to flow through that part of the circuit. And after a long time, the current will just circulate through that loop. And this is the thinking out loud part, because in thinking that you'll be ready to handle future questions, and that'll be the case. But sometimes I'll make some notes here, and they're actually answers for other parts of the problem. Similarly, with charting, when you chart out values, although I'm not going to chart out these values in total, but sometimes it's helpful in answering future parts of problems. All right, so 12 volts, that's the voltage across R2 divided by the resistance of it. Again, if you know two things, you can find the third, and 0.24 amps. All right, a long time after the switch is closed, will the magnitude of the current in R2 be greater than, less than, or equal to the current through R2 found in part D? Now, I'd said earlier that after a long time, current will not flow through that part of the circuit. So the answer is less than, and it is actually 0 after a long time, though. Okay, and if you want to get a little more specific, which they ask you to justify, once the potential across the capacitor reaches 12 volts, which is equal to the voltage supplied to that part of the circuit, current will cease to flow in that part of the circuit. All right, now the 4 nanofarad capacitor is now replaced with a 10 nanofarad capacitor, so a larger capacitor. Will the magnitude of the current in R2 immediately after the switch is closed be greater than, less than, or equal to the current in part 1 of E? Now, it doesn't matter what the capacitance is. The current will still be the same because the R2 is regulating the current, but it doesn't necessarily regulate the amount of charge that's flowing to that capacitor, and that's the point. So because you have a greater capacitor doesn't necessarily mean you have greater current being delivered to that circuit. What is being greater or more is the charge accumulating on that capacitor. So the answer is equal, and I've said as much in terms of the justification. But what I wrote here is the magnitude of current will be the same due to the resistance R2 regulating the current in the loop to the same degree. However, more charge will be delivered to the 10 nanofarad capacitor. So that should do it for the justification. All right, have a good evening.